In the following series of lectures, we are going to continue to talk about the interactions between molecules rather than what happens inside a molecule as bonds form. And in this set of lectures, we're going to look at what happens when we have two different types of molecules that are interacting rather than just a pure substance. So we're going to take what we've just learned about intermolecular forces and apply it to our foundational knowledge that we have about solutions and solubility. So diving into that, let's just start with some kind of definitions right off the bat. What is a solution? So a solution is going to be a homogeneous mixture, not heterogeneous, just homogeneous. That means when you look at it, you can't really tell you're looking at a mixture. It just looks like one thing. And any solution is going to consist of two parts. There will always be a solute and a solvent. And to tell them apart, we just look at which one we have more and less of. So the solute is always going to be whatever we have the lesser amount of, and the solvent is whatever we have more of. So when I compare my amounts with moles and mass or volume, whichever one I have less, that's my solute. Now we have a special word if our solvent is water. Then we call the solution aqueous. Uh, because a lot of solutions are actually using water as solvent, the universal solvent of life. And so we typically then just have I don't know, the genesis of having two different names for this is beyond me, but we'll call it aqueous. And that tracks with the way we represent phases as well. When we look at a chemical reaction, we tell you if it's a solid or a liquid or a gas, and we sometimes say if it's aqueous, which just means, hey, there's a lot of water around. Now, solutions come in all sorts of forms. I think the one that's most intuitive that pops in my head is things that are dissolved in water, but it can be anything dissolved in anything. You can have a mixture of gases. That's a solution. So here we've got a mixture of oxygen, carbon dioxide, and nitrogen. So that's kind of similar to air. There's a few more things added into air. So that's a solution. We can have a solution of a solid and water where the solid completely dissolves if it's an ionic compound. That would be an aqueous solution of sodium chloride. We can also have liquids dissolved in solids as well, which is an interesting one to think about. Here's mercury and silver forming a solution. The mercury is in the liquid form, and silver is a solid, and it kind of gets into all the little nooks and crannies that are made by the crystal structure, and it makes a solution. Like another example of this would be like a metal alloy where you have a solid and a solid dissolved in one another. The smaller amount of metal within the alloy would be the solute. Now, continuing on our definitions, let's look at solubility. So solubility is going to be when one substance dissolves in another, like the level at which that happens. So whenever it occurs where one thing is soluble, dissolves in another, our solute and solvent, to make that homogeneous solution, then we say it's soluble or we say miscible. These words can be used interchangeably. An example of this is table salt dissolved in water, which makes a really boring image because it's just like clear liquid. Here's cobalt chloride dissolved in water, and it makes a colorful solution. But the trick is, I'm seeing a homogeneous solution. I don't see chunks of solid and then liquid. Now, if a substance does not dissolve in another, we're going to call that insoluble or immiscible. And again, those words can be used interchangeably. The perfect example of this is oil and water. They're not soluble in one another, so they're insoluble. And you can see we have two liquids here, but they're very clearly not mixing. And you can say, oh, there's that oil bit that's yellow, and there's that clear water bit over there, and they look different based on color in this case. Now, we can actually track solubility as a physical characteristic of a compound in another compound. And you can find this information in a table. So like I can like go to the CRC handbook and I can look up the solubility in water of a lot of different compounds, and I'll get a value. It'll say like, X number of grams per 100 milliliters. And so our solubility for our solids would be measured in mass. You'll see different types of concentrations for that. But yeah, like you can go and find out how soluble something is as a physical property in another compound. We also have kind of a handy shortcut to predict the solubility of something in another compound like water, using the solubility chart that we introduced when we talked about double replacement or precipitation reactions. So a chart like this is an abbreviation. This is just like an excerpt of the chart. It says that it'll always have that ions are generally soluble or insoluble in water with a series of exceptions. So here I've shown the example of insoluble compounds. So usually we see hydroxide and sulfide ions in ionic compounds are insoluble in water. The exception is if the cation that is paired with that ion is something in group 1, like lithium, sodium, or potassium, or ammonia, NH4+. And then those solid compounds, ionic compounds, would be soluble. So it's like saying lithium hydroxide would be soluble in water, whereas something like calcium hydroxide is more likely to be insoluble. And these solubility tables are seriously shortcuts because they're not the whole picture. Solubility is a spectrum. It is not a black and white issue at all. So some things that we say are insoluble are effectively insoluble. Like some amount of them actually does dissolve in the water. It's just not that much. Things that are super soluble, some of them might actually not dissolve. Like there's a limit to their solubility. And that's what we usually track in a table when we look up a solubility value. We'll find out what's the maximum of this compound that I can dissolve in water or in ethanol or in methanol or another common solvent. And so we find that we can still predict solubility even without the shortcut of the table. The solubility of a substance we define as the amount that'll dissolve in a given amount of solvent. So it's a comparison, right? It's saying this mass of X will dissolve in 100 milliliters of water or some other solvent. And we track it and report solubility in that way. And the solubility of a compound in another compound as its solvent will depend on two different things that we'll talk about. It depends on nature's tendency towards mixing, and it depends on the type of intermolecular forces that the solute and the solvent have and how similar those intermolecular forces are. So this is going to lead us to a generalization that we call like dissolves like. So let's talk about these two. And then because we've been focusing on intermolecular forces, we're going to focus on the second one in this lecture and talk about what do we mean by a similar intermolecular forces of attraction between two different compounds. Now, the nature's tendency towards mixing is really a discussion of entropy, which we will continue to talk about throughout the chemistry series and spend more time on in 163. But let's give it a little bit of attention. So there is this tendency to mix, and what it comes from is entropy. Now, entropy is the energy randomization. That's one way to say it. You could also say it's really the dispersal of energy in a system. So the second law of thermodynamics states that energy will spontaneously disperse to become spread out if it's not prevented from doing it. Right. So the natural order of things, energy is going to disperse. And that's this driving force that is entropy, that we'll always see things spread out to disperse the energy over as large of an area as possible. So let's think about this in a few ways that might feel more intuitive, and things that we talked about before. Let's look at gases and let's look at heat transfer, things we've already talked about. So with gases, if we separate two gases with in a box, right? So they're totally isolated from one another. We've got neon and we've got argon on the other side. So they're separated. If we remove this barrier and we allow these to mix, we'll see that the gases, rather than stay on their separate sides of the container, will move to fill the entire container. That gas will occupy all of the volume that it is allowed to occupy, that it's not prevented from filling. And so that distribution of particles goes from half of it, the box, to the entire box. So it's distributed over the entire system rather than isolated in one piece. And what's happening there is that we're increasing entropy by dispersing the particles and really their kinetic energy over that larger volume. And so, really, what we're seeing here for entropy is it's the dispersal of kinetic energy within the system and spreading it out. We see this with heat too. Heat is energy, right? Heat is thermal energy. It's a subset. It's kinetic energy. And we see that heat will spontaneously transfer from hot to cold. Like when you're holding the hot coffee cup, the heat from the coffee goes to your hand and it warms your hand, which is the surroundings. What we see here is this dispersal, this increase in distribution of thermal energy. Again, just like kinetic energy. So that increase in entropy is showing the energy, that heat energy, thermal energy spread out over a larger area. And so that's entropy. And that describes that there's this tendency to mix. So if you bring two things together, there is a natural driving force for everything to mix into a homogeneous solution, unless prevented. So what would prevent that? Well, intermolecular forces. So intermolecular forces can prevent a solution from forming, or it can help a solution to form. So a solution will form if the solvent and the solute interactions, so these interactions are the IMFs, the intermolecular forces, are similar to or stronger than the separate solvent-solvent and solute-solute interactions. Now, if they're weaker, then the solution won't form. Um, or it'll only form if there is the difference in energy between them is easily overcome by that stability gained by just spreading out the kinetic energy of the system by dispersing those particles evenly throughout the system. So this requires some comparison. So the solution right here is only going to form from our particles. So we have our solvent particles right here in blue, and we have our solute particles in red. If these interactions right here between each of these are less than the interactions between the solvent and the solute. So those solvent-solute interactions need to be the same or stronger. So we're going to put into practice those skills of identifying intermolecular forces, assessing which one is stronger and kind of weighing our options, saying, oh, these are pretty strong London dispersion forces, but no, 3 hydrogen bonds. So that kind of weighing and debate that we did in the previous lectures, we're going to apply now to 2 separate molecules, one that's the solvent and one that's the solute. And we're going to compare them, and we're going to compare what happens with the interactions that would exist between that solute and solvent to evaluate if we think that we would see a solution form or if the formation of the solution would be prevented. And we'll actually talk about that in more detail in the next lecture.